Everything you see in the universe is not where it is by chance. Galaxies don't drift randomly through space. They follow an invisible structure, a hidden architecture that controls everything. This is the cosmic web.
Between every star, every galaxy, every cluster of light in the night sky, there exists something impossible. Something that shouldn't be there according to everything we thought we knew about gravity, matter, and the structure of space itself. In 2014, astronomers mapped the largest structure ever observed in the universe. It stretches across 10 billion light-years, so vast that light from one end, traveling at 186,000 miles per second, would take longer to reach the other side than our entire universe has existed. This structure forms patterns, geometric patterns, repeating patterns that mirror biological systems we see here on Earth. What if I told you that galaxies don't float randomly through space, but are threaded along invisible filaments like beads on cosmic strings? That 95% of the universe consists of a vast web we cannot see, cannot touch, but that dictates the position of everything that exists? What if the universe isn't expanding into emptiness, but is actually a living network, growing like neurons in a cosmic brain? In 1933, Swiss astronomer Fritz Zwicky pointed the world's most powerful telescope at the Coma Cluster, a collection of over 1,000 galaxies located 320 million light-years from Earth. He was attempting something revolutionary: to weigh the universe. Zwicky calculated how fast galaxies within the cluster were moving. He measured their velocities as they orbited around each other. Then he applied Newton's laws of gravitation, the same laws that predict how planets orbit the sun with absolute precision. The numbers didn't make sense. The galaxies were moving far too fast. According to his calculations, they should have been flung apart eons ago, scattered into the cosmic void like children's toys from a spinning carousel. The gravitational pull from all the visible matter, every star, every gas cloud, every particle of dust he could observe, provided only 1/6 the gravity needed to hold the cluster together. Zwicky proposed a radical explanation: Dunkel materia, dark matter, invisible mass that outweighed everything we could see by a factor of 6 to 1. For decades, astronomers dismissed the idea. Dark matter seemed too convenient, too much like inventing invisible forces to explain away uncomfortable data. Then in 1970, astronomer Vera Rubin made a discovery that would force the scientific community to confront Zwicky's ghost. Rubin studied spiral galaxies, measuring how fast stars orbit around galactic centers. Stars closer to the center should move faster, just like Mercury orbits the Sun more quickly than distant Neptune. Every prediction, every calculation based on visible matter said rotation speeds should decrease with distance. They didn't. Stars at the outer edges of galaxies were moving just as fast as stars near the center, sometimes faster. Rubin checked her instruments. She recalculated. She observed galaxy after galaxy after galaxy. The pattern remained consistent across every spiral galaxy she examined. Something invisible was pulling on these stars. Something with enormous mass distributed throughout and beyond each galaxy in a vast sphere, what scientists now call a dark matter halo. The visible galaxy we see represents merely the bright core of something far larger, something that extends hundreds of thousands of light-years beyond the outermost visible stars. By the 1980s, the astronomical community had accepted the reality of dark matter. The universe contained 5 times more dark matter than ordinary matter. Everything we'd ever observed, every star, planet, human being, every atom in existence constituted only 15% of the matter in the cosmos. But this revelation raised a more profound mystery. If 85% of matter is invisible, how is it distributed throughout space? In 1986, Valerie de Lapparent, Margaret Geller, and John Hutra at the Harvard-Smithsonian Center for Astrophysics completed the first comprehensive 3D map of galaxy positions. They expected to find galaxies scattered more or less uniformly through space, perhaps with some clustering, but generally a random distribution. What they found stopped them cold. Galaxies weren't scattered randomly. They formed enormous structures, walls, filaments, and sheets separated by vast empty regions. One structure they observed, later named the CFA2 Great Wall, stretched across 500 million light-years. Galaxies outlined something invisible, like Christmas lights wrapped around a dark framework. Margaret Geller described her reaction. "When we first saw the maps, we thought something was wrong with our data. The patterns were too regular, too organized. The universe isn't supposed to look like this." The patterns revealed the architecture of dark matter itself. While dark matter remained invisible, its gravity sculpted the distribution of visible galaxies. Galaxies collected where dark matter was densest, like pearls forming around grains of sand. The map showed not just where galaxies were, but where dark matter had accumulated over billions of years. The structure resembled biological tissue, neurons connected by axons, or cells connected by protein filaments. Scientists named it the cosmic web. But this represents just one piece of a much larger puzzle. The evidence forces us to confront an uncomfortable possibility that the architecture of the universe follows patterns we're only beginning to comprehend. Patterns that suggest the cosmos is far more organized, far more connected than we ever imagined. Between 2000 and 2012, the Sloan Digital Sky Survey mapped the positions of more than 930,000 galaxies. The resulting 3D structure revealed the cosmic web in unprecedented detail. The filaments connecting galaxy clusters measure between 200 and 300 million light-years in length. Some stretch for 1 billion light-years or more. They contain 60% of all galaxies in the universe. The filaments themselves are not uniform. They're braided structures, twisted like cosmic rope, with galaxies spiraling around them in helical patterns. In 2008, researchers led by Jörg Dietrich detected direct X-ray emissions from hot gas trapped within filaments connecting the Abell 222 and Abell 223 galaxy clusters. This marked the first time scientists observed the matter inside a cosmic web filament directly, not just inferred its existence from galaxy positions. The gas was heated to 10 million degrees Celsius, temperature created by gravitational compression as gas flows along the filament like water through a canyon. The filaments are dynamic, not static. Matter flows through them constantly. Galaxies slide along them like trains on tracks, accelerating as they approach dense nodes where filaments intersect. Between the filaments lie the cosmic voids, regions of space nearly empty of galaxies. The typical void spans 150 million light-years in diameter. Some exceed 500 million light-years. The Outes void, discovered in 1981, stretches 330 million light-years across and contains only 60 galaxies where 10,000 should exist. These voids aren't simply empty space. They're expanding. The dark energy permeating space pushes void walls outward, causing the filamentary structure to stretch and the nodes to move apart. Voids grow at approximately 1% per billion years, which means they're expanding at different rates in different directions, creating irregular, interconnected bubble structures. In 2013, researchers discovered that voids have gravitational effects on their surroundings. When light from distant galaxies passes through voids, it experiences a slight gravitational blue shift, the opposite of the red shift caused by passing near massive objects. This integrated Sachs-Wolf effect proves that voids aren't simply empty, but are active gravitational features that push rather than pull. Most remarkably, voids exhibit temperature differences. The cosmic microwave background radiation, the afterglow of the Big Bang, appears slightly colder when viewed through the largest voids. This cold spot signature allows astronomers to map void structure across the entire observable universe. Where multiple filaments intersect, matter accumulates in massive nodes called galaxy clusters and superclusters. The Laniakea supercluster, identified in 2014, contains 100,000 galaxies, including our own Milky Way. It spans 520 million light-years and contains the mass of 100 million billion suns. But Laniakea represents just one node in a larger structure. Our supercluster is being pulled toward an even more massive concentration called the Shapley concentration, which in turn flows towards something else. Following these flows of galaxy motion backward reveals they originate from specific points in the cosmic web structure. In 2020, astronomers using data from multiple sky surveys mapped the structure of web nodes extending back to when the universe was only 3 billion years old. The cosmic web already existed in recognizable form. The same patterns we see today were present when the universe was 1/5 its current age. The geometry of these nodes follows mathematical rules. Computer simulations show that nodes form where at least 3 filaments intersect, typically 4 to 6. The angles between filaments aren't random. They cluster around specific values determined by gravity's interaction with dark matter. This isn't chaos, this is architecture. But this represents just one piece of a much larger puzzle. Recent discoveries reveal that the cosmic web isn't just a passive structure, it's active, dynamic, and may be fundamental to how the universe itself evolved. In 2017, a team led by Rongman Bordoloi detected hydrogen gas flowing along filaments toward galaxies using the Keck Observatory. The gas was moving at 150 kilometers per second, gravitationally accelerating as it approached its destination. This discovery revealed that the cosmic web functions as a cosmic irrigation system. Cold gas flows through the filaments, feeding galaxies with the raw material needed for star formation. Without this steady flow, galaxies would have exhausted their gas reserves billions of years ago. Star formation would have ceased. The universe would be dark. Galaxies positioned at web nodes, where multiple filaments converge, receive matter from multiple directions simultaneously. This explains why the most massive galaxies occupy these prime real estate locations. The cosmic web doesn't just organize where galaxies form, it determines what types of galaxies can exist in each location. Researchers discovered that galaxies aligned along filaments have different properties than galaxies in voids. Filament galaxies tend to be spiral galaxies, actively forming stars. Void galaxies tend to be elliptical galaxies with little ongoing star formation. The environment determines destiny. Gravitational highways. In 2015, researchers analyzing galaxy velocities discovered that galaxies don't simply orbit within their local clusters, they slide along filaments, channeled by dark matter's gravitational architecture. Our own galaxy participates in this cosmic flow. The Milky Way moves at 630 kilometers per second relative to the cosmic microwave background. That's over 1.4 million miles per hour. We're being pulled along a filament toward the Virgo cluster, which itself flows toward the Great Attractor, a gravity anomaly representing a massive node in the cosmic web, located 150 million light-years away. But the Great Attractor isn't our final destination. It and everything around it, including the Milky Way, flows toward an even larger structure, the Shapley concentration, 650 million light-years distant, containing the mass of tens of thousands of galaxy clusters. These flows aren't random drift, they're directed motion along specific paths defined by the cosmic web's geometry. Space itself is channeled. The web determines not just where matter is, but where matter can go. In 2019, physicist Franco Vazza and neuroscientist Alberto Filetti published a remarkable comparison. They analyzed the structure of the cosmic web and compared it to the neural network structure of the human brain. The similarity was shocking. Both systems organize around similar complexity parameters. Both form networks where nodes connect through a specific number of links, typically 3 to 7. Both exhibit scale-free properties, meaning the same organizational patterns appear at different size scales. Both systems optimize connectivity while minimizing energy expenditure. The human brain contains approximately 69 billion neurons. The observable universe contains roughly 100 billion galaxies. The information capacity of the connections in both systems is remarkably similar, roughly 1 bit per connection. This doesn't mean the universe is conscious or that it thinks, but it suggests that the organizational principles governing both systems may derive from the same fundamental physical laws. Efficiency, optimization, and network theory may be universal principles that apply equally to neurons and galaxies. Most intriguingly, recent research in quantum field theory suggests that space itself may not be continuous, but rather organized into a network structure at the quantum scale, a quantum foam, where space and time form interconnected nodes. If this proves correct, the cosmic web we observe at galactic scales may mirror quantum structure at the smallest scales. The universe may be networks all the way down. Into the evidence extends beyond simple structure into the realm of cosmic evolution itself. The cosmic web isn't just where matter exists, it may determine how reality unfolds across cosmic time.
The cosmic web didn't always exist. In the first 380,000 years after the Big Bang, the universe was too hot and dense for structures to form. Matter and energy existed in an opaque plasma soup. But even then, tiny quantum fluctuations, variations in density at the subatomic level, left their imprint on space. When the universe cooled enough for atoms to form, regions that were slightly denser than average had slightly stronger gravity. They pulled on their surroundings. They grew. Dark matter amplified this process. Unlike ordinary matter, dark matter doesn't interact with light or electromagnetic forces. It only responds to gravity. This meant dark matter could begin collapsing into structures immediately, while ordinary matter remained suspended in the hot plasma. By the time ordinary matter cooled enough to collapse, dark matter had already formed a gravitational scaffolding. Ordinary matter fell into this framework like water filling ice cube trays. The cosmic web structure was already determined by dark matter's invisible architecture. Computer simulations run by the Illustris project recreated this process. Starting from quantum fluctuations and applying only known physics, gravity, dark matter, gas dynamics, star formation, the simulations generated cosmic web structures virtually identical to what we observe. No special conditions required, no fine-tuning needed. The cosmic web emerges inevitably from the fundamental laws of physics. Alternative theories. Not all scientists agree on the details of web formation. Some researchers, including Erik Verlinde at the University of Amsterdam, propose that dark matter itself may not exist as particles, but rather represents an emergent property of space, a kind of entropic force arising from quantum information stored on cosmic horizons. Others suggest that modifications to gravity itself at cosmic scales could explain both dark matter effects and energy acceleration without requiring invisible mass. Modified Newtonian dynamics, or MOND, and theories involving extra dimensions propose that gravity behaves differently at the scales where the cosmic web operates. However, all these theories must explain the same observational evidence: the rotation curves of galaxies, gravitational lensing effects, the cosmic microwave background fluctuations, and crucially, the large-scale structure we observe. Most alternative theories struggle to match the detailed predictions that standard dark matter models achieve. The scientific consensus remains that dark matter particles exist, though their nature remains unknown. Detection experiments worldwide search for these particles, hoping to observe direct interactions with ordinary matter for the first time. Philosophical implications. The cosmic web forces us to reconsider fundamental assumptions about space and structure. For centuries, we imagined the universe as objects moving through empty space, stars and planets as isolated islands in an infinite void. The reality is opposite. Space isn't an empty container holding objects. The structure comes first. Space itself is organized, channeled, shaped by the invisible matter that dominates cosmic architecture. Galaxies don't create structure, they reveal structure that already exists. This challenges our intuitions about causality and organization. We're accustomed to thinking that complex structure requires intelligent design, or at minimum, extremely special initial conditions. The cosmic web demonstrates that complexity, organization, and pattern emerge naturally from simple physical laws acting over cosmic time. The universe doesn't need a blueprint. The laws of physics are the blueprint. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct the most comprehensive survey of cosmic structure ever attempted. Its wide field of view will map billions of galaxies across half the sky, revealing the cosmic web structure in unprecedented detail, extending back to when the universe was less than 1 billion years old. The European Space Agency's Euclid mission, launched in 2023, has already begun mapping dark matter distribution through gravitational lensing. By observing how light from distant galaxies bends around invisible mass, Euclid will create 3D maps of dark matter spanning 10 billion light-years. These maps will reveal how web structure evolved over 2/3 of cosmic history. The Square Kilometre Array, the world's largest radio telescope currently under construction, will detect hydrogen gas within the filaments themselves. This will allow astronomers to observe matter flowing through the cosmic web in real time, mapping the cosmic irrigation system that feeds galaxy formation. On Earth, the Large Hadron Collider continues searching for dark matter particles. If successful, discovering the particle that makes up 85% of matter would represent the greatest physics breakthrough in a century, fundamentally transforming our understanding of particle physics and cosmic structures simultaneously. Predicting the future. Based on current observations and theoretical models, we can predict the cosmic web's evolution with reasonable confidence. Over the next 100 billion years, dark energy will continue accelerating cosmic expansion. Voids will grow faster than filaments can maintain their integrity. Eventually, filaments will begin fragmenting, isolating galaxy clusters from each other. The web will become disconnected islands in an expanding ocean of space. In 150 billion years, galaxies outside our local group will recede beyond the cosmic horizon. Their light will be so redshifted by expansion that no signal from them will ever reach us. The observable universe will shrink to just our gravitational neighborhood. Eventually, only scattered remnants of the cosmic web will remain, isolated clusters evolving independently, unable to communicate, separated by unbridgeable distances of expanding space. The grand unified structure we observe today will fragment into isolated kingdoms. Unless dark energy behaves unexpectedly. If dark energy strengthens over time, a scenario called the Big Rip, it could tear apart not just the web structure, but galaxies, stars, planets, eventually atoms themselves. The universe would end not in cold darkness, but in violent disintegration. Alternatively, if dark energy weakens or reverses, cosmic expansion could slow or stop. Gravity might eventually win, collapsing the web back toward a cosmic singularity, the Big Crunch. The web that took billions of years to form would compress back to infinity density in a reversal of the Big Bang.
The cosmic web puts humanity's cosmic address in stark perspective. We orbit a typical star in the outer spiral arm of an average galaxy, positioned along a filament connecting local superclusters. We're part of the web structure just like every other galaxy. But our position grants us a unique opportunity. We exist during the brief cosmic era when the web is visible in its full glory. We arose at precisely the right moment, early enough that expansion hasn't dispersed the structure, late enough that stars have created the heavy elements necessary for life. In 100 billion years, any observers arising in our galaxy will look out and see only our local cluster. The rest of the universe, the grand cosmic web, will have expanded beyond detection. They won't know that galaxies beyond their cluster exist. They won't know about the web structure. They won't know about cosmic expansion. We are cosmologically privileged. We exist at the one moment in cosmic history when the universe reveals its full architecture to those capable of looking up and asking questions. This realization transforms how we think about scientific observation. We're not just studying the universe, we're witnessing a temporary condition that will never repeat. The cosmic web is a gift of timing, visible only to civilizations that arise during this narrow window of cosmic history. The most profound implications emerge when we consider what the cosmic web tells us about the nature of existence itself, about organization and complexity, about the hidden scaffolding underlying everything we observe. The nature of structure. The cosmic web reveals a fundamental truth about reality. Structure exists at every scale, and each scale influences others. At quantum scales, particles exist in probability clouds until observed, connected through entanglement across any distance. At atomic scales, electromagnetic forces organize matter into molecules and materials. At planetary scales, gravity shapes spheres and orbits. At galactic scales, dark matter halos define gravitational potentials. At cosmic scales, the web organizes galaxies across billions of light years. Each level of structure constrains what can exist at levels below it and above it. You cannot understand galaxies without understanding dark matter. You cannot understand dark matter distribution without understanding the initial quantum fluctuations. You cannot understand quantum fluctuations without understanding the physics of the Big Bang. Reality is hierarchical structure all the way down and all the way up. Recent theoretical work suggests that space and time themselves may emerge from an even more fundamental structure, a quantum network of entangled states called spacetime foam, or in some theories, spin networks. If this proves correct, the cosmic web we observe at galactic scales reflects an underlying quantum structure embedded in reality itself. Space may literally be made of connections. The web isn't in space, space is a web. The information paradox. In 2018, physicist Leonard Susskind proposed that the universe may be a kind of quantum computer, with information processing occurring through gravitational interactions across the cosmic web structure. The idea builds on holographic principle, the notion that all volume of space can be encoded on its boundary surface. Applied to cosmology, this suggests that information about the entire universe may be encoded on the cosmic horizon, the boundary of the observable universe. The cosmic web structure may represent how this information organizes itself. Galaxy positions, matter flows, gravitational interactions, all of these could be manifestations of information processing occurring at cosmic scales. The web isn't just matter distribution, it may be computation in physical form. This raises profound questions. If the universe processes information through its structure, what is being computed? Is there meaning in the patterns we observe, or is it simply the universe exploring all possible configurations allowed by physical law? Some researchers suggest that increasing cosmic complexity, the emergence of structures like the cosmic web, stars, planets, life, consciousness, represents the universe increasing its information content, generating novelty through physical processes. We may be part of how the universe computes its own evolution. The simulation question. The computational perspective raises an uncomfortable possibility that serious physicists increasingly discuss. Could the cosmic web be programmed? The universe follows precise mathematical laws. These laws generate specific structures from specific initial conditions with perfect reproducibility, as demonstrated by computer simulations that recreate cosmic web structure from first principles. This means the universe operates like a simulation whether or not it actually is one. The same algorithms that govern dark matter in our universe would govern dark matter in a simulated universe. The structures would be identical. We have no way to distinguish whether we inhabit base reality or a simulation sophisticated enough to perfectly model physical law. Both scenarios produce identical observations, identical mathematics, identical structure.
The question may ultimately be meaningless. If a simulation is detailed enough to contain conscious observers who conduct experiments and discover mathematical laws, if it evolves over billions of years generating galaxies and stars and life, in what way is it not real? The cosmic web teaches us that reality is structure, and structure emerges from rules.
Whether those rules are fundamental properties of a base reality or code running on an unfathomably advanced computer becomes a distinction without difference. What matters is that the structure exists. The web is real to us because we are part of it, shaped by it, enabled by it. Our existence depends on the architecture it provides. The universe is a web of connections, matter connected by gravity, galaxies connected by dark matter filaments, quantum particles connected by entanglement, perhaps all of space connected by networks at scales we're only beginning to imagine. We are made of atoms forged in stars that formed from gas flowing through the cosmic web. We are pattern recognizers generated by the universe to observe its own structure. We are the web becoming conscious of itself. Conclusion. We began with a question: how is the universe organized? The answer reveals something far more profound than a map of galaxy positions. The cosmic web demonstrates that organization is fundamental to reality. Structure isn't imposed on the universe from outside, it emerges inevitably from the interaction of matter, energy, and space according to mathematical laws. From quantum fluctuations smaller than atoms through the patient accumulation of dark matter over billions of years to the vast filaments stretching across cosmic scales, the universe built itself into a web of connections that spans observable reality. We've discovered that galaxies slide along dark matter highways, that voids expand and push their surroundings, that matter flows through invisible channels feeding the formation of stars and planets, that the web's architecture follows the same optimization principles that govern neural networks in our brains. The scientific consensus is clear. The cosmic web exists. Dark matter forms its scaffolding. Ordinary matter reveals its structure, and that structure determines where and how galaxies evolve across cosmic time. What remains unknown is equally fascinating. We don't know what dark matter particles are. We don't understand why dark energy accelerates expansion. We can't yet observe the web structure at quantum scales or predict how web evolution might surprise us in billions of years to come. But we know the web is there. We've mapped it, we've measured it, we've watched galaxies slide along its filaments in real time. The universe has revealed its hidden architecture to those willing to look deeply enough. Perhaps the most remarkable truth is this: you are part of the web. The atoms in your body were forged in stars that formed along web filaments. The galaxy containing your world slides along web structures at over 1 million miles per hour. You exist because the web exists, because dark matter created gravitational potential wells where gas could collapse and stars could ignite. The cosmic web connects every point in space to every other point through gravitational influence propagating at the speed of light. In a very real sense, every galaxy is connected to every other galaxy through the web. Every star touches every other star through gravitational threads too weak to measure individually, but collectively strong enough to organize the cosmos. You are a pattern within patterns, structure within structure, connections within the greatest network ever observed. The universe is vast. The mysteries are endless. The web connects everything, and the journey to understand continues.